Well, it's a great pleasure to welcome our next speaker for the afternoon, Matt Gursky from Notre Dame. He'll be telling us about critical metrics on connected sums of Einstein four-manifolds.
Okay, thank you very much, Claude. And let me begin by thanking the organizers for the invitations. Great privilege to speak at the Geometry Festival. So this is joint work with Jeff Viaclovsky. Let me say that at the beginning, because I don't actually state the result till much later in the talk, so I want to get that part settled. And then let me begin by saying what we mean by critical, and I'll go from there. So everything in this talk happens in 4 dimensions. So let's take a smooth closed four-manifold. Oriented will be convenient, because all the examples I'm going to consider, well, for the simplified version of the talk, everything will be oriented. So by critical, I mean we're going to mean a metric which is a critical point for the quadratic Riemannian functionals. So these are the functionals which are integrals of quadratic polynomials in the curvature. So the simplest example you could imagine would be take just the norm squared of the full curvature tensor and integrate it over the manifold. You could also look at different components of the curvature tensor. So you can contract and just say, look at the integral of the square norm of the Ricci tensor. And then also look at the, contract the Ricci and get the scalar curvature. So you can look at these 3 would be a basis for all the quadratic curvature tensors. Now, you could also just replace the first one, and this is what we're going to do, by the integral of the norm squared of the vial tensor. So those 3 will be the basis, and we're interested in critical points of these kinds of functions.
Strictly speaking, W plus is a different one, right? So.
Yeah, okay, all right. So now on the other hand, the 3 I just listed, though, are linearly dependent. So the Chern-Gauss-Bonnet formula says that this particular linear combination gives you the Euler characteristic. So therefore, you may as well just look at the linear combination of any 2. I'm just going to look at linear combinations of vial squared and scalar squared. I can replace the Ricci squared. And also, you could argue that, well, this isn't completely general because you could consider just the integral of the scalar curvature squared alone. But there's reasons why that functional isn't quite as interesting to us. That will be more clear later. So in any case, I'm going to look at the general functional, which is given by this following formula. Look at the norm squared of the vial tensor, and then any multiple you like of the integral of the scalar curvature squared. Okay. Now, so formally anyway, if you want to think about it, if this bothers you, if take t equals infinity, then that would just say correspond to the integral of scalar curvature squared. Okay, so let me begin by considering the case where t equals 0. So this is referred to usually as the vial functional. So this is the integral of norm squared of the vial tensor. Now this has a number of interesting properties, the first of which is that it's conformally invariant. So multiply the metric by any positive function, it doesn't change the value of the functional. So if I find a critical point, in fact I've found infinitely many critical points because I can just multiply by, but I can just look at any metric in its conformal class. Now the gradient was calculated back in, I guess, the 1920s by Bach. So thus it's called the Bach tensor. So one of the properties of these quadratic functionals is that the Euler equation is going to be 4th order in the metric. So if you just do a first variation, you'll have to integrate by parts, and all the Euler equations will be 2nd order in the curvature. So that makes them quite complex. So this is the formula for the Bach tensor. As you see, there's 2 contractions of, well, you take 2 covariant derivatives of the vial tensor and then contract. So it's basically 2 divergences. And then you have a term where you contract the Ricci tensor with the vial tensor. So when this is 0, metrics are called Bach flat. Okay. Now, what are some examples of Bach flat metrics? Well, the first thing, by the way, to point out is that not only is the functional conformally invariant, but the Bach tensor is conformally invariant. That doesn't follow immediately from the invariance of the functional, but it happens to be true. So, and this is the scaling. If you multiply the metric by a function, then it scales this way. So the Bach tensor changes by 1 over that function. Now, so here's a first example. So any Einstein metric will be Bach flat. So this is a consequence of the second Bianchi identity. So if you look at the second Bianchi identity and see what it tells you about the vial tensor, so in particular, just write out the decomposition of the curvature tensor, you'll see that the divergence of the vial tensor is 0. So that first term in the formula for the Bach tensor will vanish. So remember, there's two terms. There's this double divergence of the vial tensor. Then the second term was the contraction of the Ricci tensor with the vial tensor. But if the Ricci tensor, because of the Einstein condition, is a multiple of the metric, and then when you contract, since the vial tensor, all its contractions are 0, the second term will be 0 as well. So it's just a pointwise calculation. These are critical points. And then again, because of conformal invariance, anything which is conformal to an Einstein metric will also be Bach flat. Now, there are other examples. So now, since our manifold is oriented, the bundle of two forms splits into the subbundle of self-dual and anti-self-dual two forms. And so this is, you have to check some things. This is all well known that this induces a splitting of the vial tensor into endomorphisms of these subbundles, so we call them W plus and W minus. And we say that a manifold is self-dual or anti-self-dual if the vial tensor, W plus or W minus, W minus or W plus vanishes. So examples would be any conformally flat manifold, the vial tensor vanishes. So these two parts will vanish. So those would be examples of such manifolds. But also, say, CP2 would be an example of a self-dual manifold. Okay, now why are these relevant to Bach flat? Because of the signature formula. So the signature formula tells you that the norm squared, the integrals of the square norms of the two pieces of the vial tensor, this gives you an index, right, for, well, anyway, so you get the signature, the Herzberg signature formula relates okay, so go back to the cut product. Well, let me just tell you the formula. So anyway, the signature formula tells you the integral of W plus squared minus W minus squared is topological. So anyway, if you rewrite the integral of vial squared in terms of the two components, what this tells you is that anything which is self-dual or anti-self-dual is a global minimum, in fact. So necessarily, they're Bach flat if they're minima. Now, so this is a variational argument, but in fact, there's a way to do this. Check this locally. You can rewrite the formula for the Bach tensor. There's a way to do that and just use the vanishing of either piece of the vial tensor to show that this is true just by looking at the Euler equation. You don't have to argue just variationally, but it's easier to see this way. Now, I don't want to go into self-duality. It's a huge subject. So let me just mention that the kind of gluing construction that I'm going to talk about here in a minute has been quite successful for constructing, say, self-dual or anti-self-dual metrics. And this list here is very selective. It's more just some of the gluing results that are related to what we're going to do. But in any case, I just also want to point out that in addition to being successful, it's the beautiful mathematics. But for us, it's been useful to read through all these papers. But on the other hand, I want to emphasize that constructing this problem of constructing self-dual metrics is second order. So you're trying to make a piece of the curvature vanish. So it's a second order condition in the metric. Whereas if you look at more general, say the Bach flat condition is a fourth order condition. Okay, so technically, it's going to be quite different what we have to do. Now, I'm always a little hesitant to make this point because I'm actually hoping I'll be corrected on this. But at least to my knowledge, and I keep asking experts, the only compact examples of Bach flat manifolds that people can write down explicitly are either self-dual, anti-self-dual, or Einstein. These are the only ones I'm aware of. So what Jeff and I originally set out to do, in fact, was to try to construct Bach flat metrics by new examples, by gluing procedures. But we ran into a difficulty that led us to consider more general functionals. So let me now begin to explain what we did. So back to this, the functional with an arbitrary value of t. So we're looking at the integral of vial squared plus t times this integral of scalar curvature squared. So I already told you about the gradient of the vial functional. So now let me talk about the second part of this. So if you look at the functional which assigns to any metric the integral of the square of the scalar curvature, you can do a first variation calculation Again, it's going to be fourth order in the metric, so the leading terms there are just different. You have the Hessian of the scalar curvature and its Laplacian. And then you have some terms in the scalar and Ricci curvatures. So that's the gradient. So if that's the gradient, what are critical points of this functional? So you can just check. Critical points are either Einstein metrics or they're scalar flat. Right? So setting aside the scalar flat condition, in general, if you're looking at critical points of the integral of the scalar curvature squared, it's the same as the critical points of the total scalar curvature. So that's one reason why we're not as interested in this function. It's not, the critical points are already known for the case of the total scalar curvature. So let me just explain very quickly. So the Einstein condition. So you, if you have a critical point, then this tensor vanishes. So if you take the trace, what ends up, you see quickly that the last term involving the Ricci and scalar curvature is trace-free. So it tells you that the scalar curvature, well, the scalar curvature is harmonic. So we're in a closed manifold, so you have constant scalar curvature. So if that scalar curvature is 0, you can just check that this tensor vanishes. So obviously, that has to be true, because that would be a minimum of the functional, right? Because if you're integrating the scalar curvature is 0 needs to be a minimum. On the other hand, if it's a non-zero constant, then the first two terms involving the scalar curvature are gone, but then the last term is just a multiple of the trace-free Ricci tensor. So very simple to see. So you have two functionals. One, the critical points are scalar flat or Einstein. The other one is this Bach flat condition. So when you combine them into this functional, we call B superscript t. So the gradient for that is the Bach tensor plus t times this tensor. We called it C just because it was the next letter in the alphabet. I don't think it has a name. So this is the condition we're trying to solve. We're trying to construct metrics for which the Bach tensor plus t times this other tensor is 0. Okay. If this holds, we say these are BT flat metrics. So instead of Bach flat, BT flat. A BT flat metric for t equals 0 would be Bach flat. Excuse me. Now, what does it mean? Well, it means what it means. But here's one thing you can say: if it's BT flat, then in particular it has to have constant scalar curvature, and this formula here tells you one way to think about it. It basically says that the Bach tensor is just a multiple of the trace-free Ricci tensor. If t is non-zero. If t is non-zero, that's right. So if t is non-zero, this will be the case. Of course, if t is 0, it's just Bach flat. But in general, this is what it means if you're BT flat. So, so why is this true? Well, if you trace this equation, the Bach tensor is trace-free. So when you trace this, you just get the same condition that you had before, namely that the scalar curvature is constant. So if the scalar curvature is constant, the first couple of terms in this formula for this tensor C goes away. So anyway, the resulting condition is exactly this, that the Bach is a multiple of trace-free Ricci. And that multiple is given by t times the scalar curvature, well, 2t times the scalar curvature. So this is the sort of geometric meaning of this condition. There's a relationship between trace-free Ricci and Bach. Okay, so what are examples of BT flat metrics? So Einstein metrics, because they were critical for both. They're both Bach flat and obviously critical points of the integral of scalar curvature squared. Also, if it's Bach flat, then the first piece is 0, and if it's scalar flat, as we pointed out, then the second piece is 0. So anything with Bach flat and scalar flat will be a critical point. So here's the goal. We want to take two Einstein four-manifolds, because we know those are BT flat, for any value of t you like, right? And see if we can glue them together to produce a new example of a BT flat metric. Okay, so here's the catch, which sounds strange when you first explain it. So let me push the precise statement a little later on in the talk. We can't specify a priori what the value of t is going to be. So we basically construct an approximate solution, but in order to perturb it to get an actual solution, we have to have the freedom to move the parameter t a little bit. So that's why we can't specify it at a time. On the other hand, so careful, this is always going to be vertigo when people do this. Let me do this slowly. Okay. So this condition here that your BT flat means the Bach tensor is a multiple of the trace-free Ricci. That condition, well, it holds for any value of t. In other words, if you think about just generally speaking, the condition just means that Bach is a multiple of trace-free Ricci. The value of the parameter t doesn't seem to have much significance if you think about it in these terms. So in that sense, maybe this inability to specify t ahead of time is not so serious. Okay, so let me give an overview of the gluing procedure. And then as various difficulties begin to arise, then it'll make more sense when I finally state what the final result is. So I should say that all gluing results are the same and all gluing results are different. I mean, somehow the scheme is sort of the same, but there's some anticipated difficulties you run into that people, if you do gluing for a living, you sort of know in advance that this is something you're going to have to deal with at each step. So each, on the other hand, each individual result is a little idiosyncratic. But so let me set things up a little bit carefully here to explain what we run into. So okay, so here's the setup. Let's let y and z be our two Einstein manifolds. Later on, I'm going to give a very short list of the ones that we need to choose. Since they're both Einstein, again, they're BT flat for all values of t. So we already have two critical points, right? Two solutions of the equation. And we glue them together to get a new one. And these are going to have positive scalar curvature. That'll be important at various phases, but in a minute, very important. So let's fix 2 points, though, 1 point in each. So these are going to be our gluing points. And we're going to look for a constructive metric that satisfies our condition on the net sum. Okay, so here's the first step. We want to do a conformal blowup. So we specified that each of these has positive scalar curvature. So what I want to do is take the first one, y, and I'm going to blow it up by a conformal factor. So since the scalar curvature is positive, the conformal Laplacian, this is the linear operator which measures how the scalar curvature changes, basically. It's a linear term in the transformation formula. This operator will be a positive operator. And therefore, it's standard that its Green's function will exist. So you can specify, and we're going to choose the Green's function with pole at the gluing point y0. Okay? So in other words, the function g, away from the point y0, it's just a solution of LG equals 0. Globally, it's a distributional solution. Right? LG equals the Dirac delta. But anyway, point y is away from the gluing point. LG will be 0. It's going to blow up at you have a fairly precise rate at that point, basically 1 over the distance squared, because we're in 4 dimensions. And it's a positive function. So what we do is quite standard. We take this Green's function and we use it to define a conformal metric, which I'll call Gn, n for neck. I'll have some pictures in a minute. So we're going to blow it up, call this new metric Gn. It'll be complete. And what's important for us is that it's scalar flat. So that's why we chose the Green's function for the conformal Laplacian. So this last line here is just the formula which tells you in general, if you conformally change by a function capital G this way, what the resulting scalar curvature is. So since it's the Green's function, the resulting scalar curvature is 0. Okay, so we replaced our compact manifold y. We puncture it at a point, blow up using this Green's function. Okay, now we started off with an Einstein manifold which satisfies our equation, but now we've done this sort of violent conformal change. Did that cost us anything? And the answer is no, because Einstein condition meant that the compact manifold y was Bach flat, and we've just multiplied by a conformal factor, so that's an invariant, conformally invariant condition, so it remains Bach flat, the metric Gn, but it's also scalar flat. So it's Bach flat and scalar flat, so it's a solution for each piece of the Euler equation, the B piece and the C piece. So we're allowed, in this case, to blow up to get find another critical point. Okay, so this metric Gn is Bach flat, is BT flat, but it's also asymptotically flat. So you can take inverted coordinates. So you could imagine y are normal coordinates near the blow-up point, and you can invert those. This gives you a coordinate system near infinity for the manifold M. And in those coordinates, this is asymptotically flat metric of order 2. So it'll look like the flat metric plus a term which decays quadratically. Okay, so we've blown up the first one, and we want to glue it to the second one. So here's the picture. All right. So we started off with our two compact manifolds. So and then Y was the one we blew up. So now it has this end, which looks asymptotically Euclidean. By the way, my student Lynn, who's in the audience, did these pictures. I stole them from her talk because in her thesis she did a gluing problem, so they were ready-made for me. So so here's the current picture. Now this right away you see a problem. So we have the end of the asymptotically flat manifold. The curvature is almost 0, but we haven't done anything to the other compact manifold, which now has curvature, say, about 1. So they're at very different scales, so we have to do something if we're going to try to combine these some way. So and here's just a slightly more careful way of saying what I just did. So Gn is flat near infinity, and which is identified with the gluing point. So if we're going to somehow glue the two manifolds and the two metrics together, somehow we need the metric on the compact piece to be almost flat near the other point. That's a typo. It shouldn't be P2. It should be Z0 in the previous. So here's what we do. We're just going to scale up. So we just take the compact manifold and we multiply by. We take two tiny parameters, call them A and B, and you multiply the compact metric GZ by A to the minus 2 B minus 2. So you scale it way up. So this is supposed to be a view from like 10 miles away. You have the original asymptotically flat manifold. Now we take the compact one, scale it way up. And of course, when you scale it way up at each point now, the curvature is almost 0. So now we're going to be able to do some kind of gluing procedure. It won't be too violent because near the gluing points, they both will be roughly flat. Okay, so here's how we do this. I'm going to set this up a little bit carefully. The idea is fairly simple, but I want to set it up slightly carefully because I want to point out there's an important consideration even at this stage. So what we do is on the compact manifold Z, take a tiny annulus, and then when you scale it up, it's going to, if you scale it up by the parameters I just listed, it'll be about size 1 over A, 2 over A. And on the asymptotically flat piece, we just take an annulus near infinity of inner radius A inverse, outer radius 2 A inverse. So this is the picture. So you take a small annulus on the compact piece, and when you scale it up, now it's a big annulus. And on the asymptotically flat piece, you take some big annulus of that size. And then we just want to identify along these annuli, and that's how we're going to glue them together. Okay? So again, this is pretty standard stuff. So this is identification map between the two coordinate systems, which allows us to, there's a little abusive notation here. You're going to pull back via the coordinate system to identify them. But in any case, this is, the picture basically tells you what's going on here. So you've done this identification along these annuli, and now you have the kinetic sum of the two manifolds. Okay, so that tells you how to construct, using this coordinate system, the kinetic sum in a precise way, but we got to glue the metrics together, right? So how do you do that? All right, so here's the naive way you'd want to try to do this. Now on each piece, the compact piece and the asymptotically flat piece, they already satisfy the equation that you're trying to solve, so you should just leave them alone, right? So the metric you glue together should be, let's call it G sub AB, because it depends upon the choice of those two small parameters. You should just leave the metric alone up to the annulus in the asymptotically flat piece, and on the compact piece that you've scaled up, as long as you're not too close to the gluing point, you should leave that metric alone. And then on the overlapping region, you should just say use cutoff functions or something to glue the two metrics together. Okay, so so if you do that, then you can compute, and sure enough, this tensor, B plus TC, the BT tensor, sure enough, it'll be quite small in this transition zone. So this B plus TC is 0 in each piece. So the only question is, what is it equal to if you sort of glue these two using cutoff functions on the annuli, on the annuli that you identify with one another? So if you just do a back of the envelope kind of calculation, this is the size of this tensor. So it's small. If A and B are small, this is clearly small. But the problem is it's not small enough. And I don't expect you to look at this estimate and nod knowingly that it's not small enough. But it turns out that when you do some of the calculations later on, you realize that this is not going to cut it. So this is kind of a crucial point, but it's highly technical, and I don't want to write everything down carefully. Let me just say roughly what the idea is. So on the neck piece, you're looking at, we're just going to look at this annulus where you do the gluing. So on the neck piece near infinity, it's equal to the flat metric plus some error. Okay? And same thing, when you take the compact manifold, you scale it up, I call that G tilde. When you restrict to that annulus, it's the flat metric plus some other error. All right. So the obvious thing to try to do is just take this metric. You want to glue the two metrics together. Well, they're both some perturbation of the flat metric. So on this annulus, you should just take it to be the flat metric. And now just do something with cutoff functions that transition from this to this. I don't know, something like 1 minus a cutoff times the first error plus a cutoff times the second error, something like that. But this is just too crude. You get too many error terms when you do the calculations. So instead, you have to do something more subtle. So here's the rough idea: is go back to the formula for the neck metric. So it's flat. It's asymptotically flat of order 2, so there's something which decays inverse quadratically, and then there's, and this is completely explicit, by the way. This is just based, this you can write down what this is in terms of the curvature of the base point. So in any case, this is known. There's some higher order terms in the expansion. And same thing with this, the scaled up compact metric. Call this H2, because this will also be quadratic, and then you scale it up. The problem is, it's great that they, the idea of doing this is that, look, they agreed to first order, so let's just patch together the errors. But that's not good enough. So the idea is that you would like them to match to the next order up. Okay, now they don't necessarily. So what you have to do is do a perturbation which is global. So you do a global perturbation of the metric, and you change the expansion to this. I'm not telling you how you do it, but let me just tell you what the punchline is. And you change the expansion over here so that these now match. All right? So you wiggle this metric, so its expansion here matches the expansion over here. You have to wiggle them sort of simultaneously, but you do it in such a way that they match up to the next order. Then, now that they match up to the next order, then your cutoffs only hit up to these error terms. So you get when you compute how close you are to an actual solution, your error term is much smaller. Okay. Now there's another subtlety. Okay, so why is it necessarily better? So if you look a little more carefully, here's the idea. Let me abbreviate B plus TC is just B sub super T. So you want to compute this for this patch together metric. So suppose you do this procedure. Again, I haven't been too careful to tell you how you exactly wiggle these two metrics. So what's the idea? So if you want to compute it, it's basically just like a Taylor expansion calculation. This is still going to be the flat metric plus some error. Okay? So if you expand this, this will be this tensor at the flat metric, which is just 0, plus the linearized operator applied to this error term, plus some higher order terms. So if you really wanted to get the metrics to match well and have this tensor be very small, you'd really like to do the wiggling to make everything in the kernel of the linearized operator. Right? This is kind of standard. We learned about this, by the way, I should give credit to, by, in a paper of Olivier Bicard. So he did a beautiful paper where he glued in Iguchi-Hansens into orbifolds, into Poincare-Einstein manifold orbifolds. And learned this trick from him. But the idea is you do this wiggling in such a way that you try to hit the kernel of the linearized operator. There's obstructions to doing that, but you have to pay basically a price for it. But this is the essential idea, is that you can't, if you just use cutoffs crudely, all the norms are too big, so you have to really go back and and carefully look at the behavior of the linearized operator in each piece when you do your when you sort of do your flattening out. Okay, so anyway, however you do it, eventually you construct a metric on the connect sum, which should be close to a solution, and now you want to perturb it. Okay. So here, then the next step is to define a nonlinear map whose zeros will give you solutions of the problem you're trying to solve. Okay. So we think of this metric G sub AB as being an approximate solution. We're just going to add a small perturbation, I call it theta here. And what we'd like to have so that GAB plus theta, that this be a metric, so theta has to be small, right? And it kills this term B plus TC. So that's what we'd like to do, but we have to add a term here, okay? Because if you just look at this, if you were just to ignore the second term in this formula, whatever it means, and just look at this BT tensor acting on the metric plus a perturbation, if you linearize that, it would not be elliptic. This is completely standard. So this condition is invariant of the diffeomorphism group, so the linearized operator is going to have degeneracies in its symbol. So in order to make it elliptic, we add another term. Okay? So this is, if you're familiar with people who study like the linearized Einstein equations, this second term, usually it's the lead derivative operator acting on section. So what we're doing is using the conformal killing operator. So we add a term which looks like conformal killing operator acting on some third order differential operator. I won't write out what it is, it doesn't really matter. But it's designed in such a way that when you linearize this operator P, the resulting operator is elliptic. Okay, so this conformal killing term compensates for the degeneracies in the symbol. Okay. So I call this thing gamma because it's for gauge fixing, so, to make sure that we get ellipticity. So you have the term you're really trying to kill, plus you have to add a term which takes care of the gauge. Now, gauge invariance. Now, of course, now you worry that you've just added a term to your equation. If you find a zero of this, are you really finding a zero of the equation you want? And the answer is yes. So here's the statement. So first of all, just notationally, let's let S be the linearized operator. So we're going to linearize at 0. We think of 0 as being almost a solution, so we linearize at that point. Call that S. And so here's the two main observations. So first of all, if theta is small and you have a 0 of this map P, then in fact it's a BT flat metric. It's a 0 that you're actually looking for. So the gauge term doesn't mess anything up. On the other hand, the gauge term helps you because now when you look at the linearized operator, you now see that it's elliptic. Okay, so now we have a nonlinear map. It's elliptic, so we can start using elliptic theory. That's good. Its zeros correspond to metrics which are going to be satisfy our fourth order equation. So we're ready to roll. So now how do we find the zero nonlinear map? Well, it's a perturbation result, right? We're already saying that we should be very close to a solution to begin with via the gluing. So we want to try to use some version of the implicit function theorem. So to make this work, what you need is you need surjectivity of the linearized operator. And then you can set up a fixed point argument and catch an actual 0. And the idea is that you want to show that when these parameters A, B are small enough, the linearized operator is surjective, and you can control its norm independent of how small the parameters are, and then set up a fixed point argument and catch a 0. Okay, so how do you prove surjectivity of the linearized operator? Well, there's various ways to try to do this. We do something which is, appears quite a bit in literature, which is basically a limiting argument. So basically we say, well, look, if it's not surjective, you have a co-kernel, then what you do is you let these parameters get smaller and smaller, and if you always have a co-kernel, you can just take a limiting argument and try to argue that that co-kernel in a limit will have to converge to something non-zero either on this neck piece, the N manifold, or the compact piece. So in other words, what we really need to do is understand the linearized operator on the two pieces. So we need to understand the linearized operator on this asymptotically flat piece, and also on the compact manifold, the puncture, where at the gluing point. Now, I'm also going to, it turns out this is also kind of standard, but I don't want to get into this because it makes things highly technical as you describe all your function spaces. We're going to work in weighted function spaces, and the weight we're going to choose, and you fix some point in the glued manifold and use that and measure distances from that point, and that'll introduce a weight. But I don't want to get into that. It's too technical. But it's hiding in the background of what I'm going to say about the linearized operator. So we have to study the linearized operator on these two pieces, and the bad news is, just in general, the co-kernel is going to be non-trivial. It's just a fact of life. Okay. So in fact, when we first started working on this problem, especially when we were looking at the Bach-flat case, when we really were trying to glue Bach-flat metrics, we decided to try to understand a concrete case very carefully before we try to do anything more general. So we took a compact manifold, we blew it up conformally, we looked at the linearized operator, everything was explicit so we could separate variables and do everything by hand and look at the co-kernel. And it was, the dimension of the co-kernel was huge. You could enumerate everything and understand geometrically for the most part, what they all represented. But we realized very quickly that trying to do this in general was going to be almost hopeless unless we started imposing some additional conditions. So the first way to cut down on the co-kernel is to impose symmetries. So this will cut way down on the dimension. So we're going to do equivariant gluing. Now it's time to be a little more careful about the Einstein manifolds we're trying to glue together. So we're going to take CP2 or S2 cross S2. So those are both positive Einstein manifolds. And so the symmetries we're going to impose are the following. They each have a torus action. So we're going to glue among toric metrics. All right? And it turns out that this will radically reduce the co-kernel that we have to work with. And in addition, there's one other action. Let me just mention this for S. You can make it explicit for both, but I mean it's easier to see for S2 cross S2. There's a Z2 action, which is just basically interchanging the two S2 factors. Right? So that'll be important as well. So from now on, we're going to assume all these symmetries. So all our function spaces, any bundle we work on, any function space we work on is going to be invariant on these two actions. Okay, so back to this question of how do you understand the linearized operator. So here, let's look at each piece. Let's look at the compact piece first. What do you know about the linearized operator there? All right. This is actually related to some work we did a few years before where we were looking at Einstein metrics and trying to understand their stability properties. So anyway, as a corollary to some of that work, what we can prove here is, or what we proved there but applied to this problem is the following, is that as long as the parameter t is negative, then the co-kernel of the linearized operator is just given by multiples of the metric. And geometrically, this just comes from scaling. So you can scale the other piece all day long and just have to adjust that parameter b. So there's this kind of ambiguity in the degree of freedom in the problem that leads to this co-kernel element.
Why is the sign of t complete?
Yeah, you just have to calculate. When t is too big, so for the so if you take the S2 cross S2, well, I don't think it matters because either way it's very complicated. You can write down an explicit formula for the linearized operator in these two cases and just check what happens for a given value of t. And there is a range of t where the linearized operator will have no kernel. Okay. And if you go too far out of that range, you can pick up a kernel element, it turns out.
I mean, it's like looking at Laplacian plus t, right? I mean, you know the sign of t that matters. If t has a favorable sign, if there's no kernel, if it has a bad sign, you can get in trouble.
Yeah. So in fact, it's a little better than t negative, but eventually I'll be working with t negative anyway, so it's just easier to state it that way. By the way, there is another co-kernel. If you're looking at the S2 cross S2 case, another thing that should be in the co-kernel is the element you get. Geometrically, you can think about scaling the two S2 factors independently, but that's not invariant this other this Z2 action of interchanging the two factors. So there's a symmetry which immediately gets rid of something like that.
But this statement doesn't depend on the symmetry. This statement about
This actually does. Yeah, this actually does.
So this is the equivariant term.
Yeah. That's why I said from now on everything is assuming all the symmetries. Yeah, because the problem is that some of the statements I'm going to make will depend upon the symmetries. Sometimes they won't. I don't want to get into that. So. Okay, now, but this is the much more interesting case. What happens when you do this conformal blowup? All right. So down in the compact piece, this, as I mentioned, Jeff and I studied the compact case, looking at the linearized operator a few years ago. So now you've conformally blown up, and you wonder, what relation there might be between the co-kernel sort of upstairs versus downstairs. So here's the statement. So let's look on what I call the neck, N, or we call the neck. So suppose you have something in the kernel of the linearized operator. Split it into two parts. So Z, which is the trace-free part, and then this function F, which is the trace part. So then what you can say is the following. Then the trace-free part is given exactly by the conformal killing operator acting on some one form. And this function F has to satisfy a certain equation involving omega. So you get this, in some sense, you decouple the two pieces, but it is a coupled system, right? But anyway, at least you get to study Z and F separately now somehow. So, and this is absolutely crucial, and it depends in a very important way on the conformal invariance of the Bach tensor, it turns out. So basically, what we do is we end up showing that Z lives in the kernel of the linearized Bach tensor, and then we end up showing that it has to be given by a conformal something in the image of the conformal killing operator. So, but that uses the conformal invariance of the Bach tensor quite explicitly. So anyway, the point is, we know what the co-kernel is now, and you know about this omega 1. What you also know about is that asymptotically, it just looks like the dilation vector field. So geometrically, this is just accounting for the fact that near infinity, you can kind of imagine that if you take this sphere and blow it up conformally, what do you get? You get Euclidean space, right? You can dilate in Euclidean space. So on this asymptotically flat manifold, asymptotically, you have this sort of dilation action that's accounting for omega. And then you can expand out F and see that F is a constant plus something which decays quadratically. So anyway, so we know what our co-kernel is. We have to live with. We have to live with this co-kernel on the neck, which looks like this, but it's more or less explicit. And then there's a co-kernel on the compact piece, which is just a multiple of the metric. Okay, so what we do is, all right, when we go back to the glued manifold, what we're going to do is cut off those two, so each of those co-kernel elements, one lives on the neck N, one lives on the compact manifold Z. Let's cut them off so that we can sort of artificially put them on the glued manifold. So we think about those sort of being approximate co-kernel elements. So if you do this limiting argument I mentioned before, where you say, well, if I look at the glued manifold and I look at the linearized operator, and I run my parameters very small, if I have a co-kernel element, it's going to have to begin to look like one of these two, is the idea. So if you take these two, you cut them off and you put them on the manifold, then they're basically going to be approximately equal to the actual co-kernel of the linearized operator. So once you cut it off, call the first one. This is just taking the co-kernel on the co-kernel element on N and just cutting it off, and call that K1 when you put it on the glued manifold. And then K2 is just the one coming from the compact piece. That's just a cutoff function times the metric on the compact piece. So those are your two co-kernel. Well, they're approximately in the kernel of the linearized operator. So what this means is, and this is kind of standard, if you can't quite solve your equation because of a co-kernel obstruction, you can, if you set things up correctly, and you can solve modulo the co-kernel. So that's what we do. So we show that it's possible to find not necessarily a zero of this nonlinear map P, but we can find something so that the image of P is in the span of these two approximate co-kernel elements. Okay? So that's what the implicit function theorem gives you. All right, so now, so it's sort of good news, bad news. At least we have an equation to work with. but the bad news, it's not a 0 like we'd like. So now the magic of this extra parameter t comes in. All right. What we want to try to show is that you can actually kill off those two constants, lambda 1 and lambda 2. So how do we do that? The key one, it turns out, is lambda 1. So let me back up. So it turns out if we can show that lambda 1 is 0, then it turns out that lambda 2 is easy to show that it's 0, because just the structure of the equation tells you that you can't have something of the form function times the metric in the image of p. So anyway, the second part is not the issue. It's that first term you want to try to kill off. So here's really the sort of the key proposition in the whole paper, and it's just a very long calculation. It turns out that when these parameters, so first of all, to simplify, I chose A and B to be separate parameters in the setup. And part of that was just to emphasize that the two co-kernel elements come from like a dilation versus a scaling, and those sort of are tied to the choice of the parameters A and B. But anyway, we can just take A to be equal to B from now on. Okay, so set them equal to one another. Then we have one gluing parameter A, and it turns out that you can write down, for A really small, you can write down an expansion of this first term, lambda 1. It's just some constant times A to the 4th plus something which is smaller. So say it's big O A to the 5th. Okay? And you can compute this constant mu explicitly. So when you compute it, what you find out is that you have terms which are come from interaction of the curvature in the two pieces in the gluing zone. So you end up fixing remember you fix the two gluing points, but you also fix coordinate systems and then do this identification map. So you can treat the tangent spaces at the point y naught and z naught as being the same thing. And so you have the same coordinate system. So you can view the vial tensors as living in that coordinate system, and tensors on the tangent space at the same point. So you can just take you can just contract them and take you could take the tensor product and take all possible contractions. All right. So it's like the inner product of the vial tensor, even though a priori they live in different universes, right? When you do the gluing and identify the points, they live in the same tangent space. So this is just the tensor product and then traced.
Can you remind us of the relation between y naught and z naught?
Yeah. Let me. Yep. Sorry. Yeah. There's a lot of. So I'll just draw the picture here. So you start off. What did I do with the chart? Yeah, here we go. So you begin with y here, and the gluing point y naught, and z here, and the gluing point z naught, and then you blow this one up.
Basically, what, an orientation reverse an identification of the tangent space?
Yeah, you have to do that. That's right. Yeah. So this is supposed to, well, this is my awful attempt to draw something which is asymptotically flat, but it's supposed to be a Euclidean end. And in your Euclidean end, you choose, you have an annulus here, roughly of size A inverse. A inverse. And here, you have a small annulus, and you scale up. So now this manifold over here is huge, and a big annulus here. So anyway, this is the vial tensor on the manifold y at that gluing point y naught, the vial tensor on z at the point z naught, and you just take their inner product.
So does W plus of y interact with W minus of z?
Yes. So of course, yeah, right. That's the whole point. Yeah, the interaction. You have to be careful with that when you do these calculations. Yeah, that's right. And then what ends up happening too, because when you do the asymptotic expansions of the metric, the asymptotically flat metric, you pick up the mass of the manifold Gn. Okay. So that ends up coming in as well with a t in front. So that's the sort of wonderful thing that happens is this parameter t shows up only in this term with the scalar curvature of the compact piece and the mass of the asymptotically flat manifold. So what this means is that when A is really, for all A small enough, you can always choose a t that'll kill off lambda 1. All right?
It's the ADM mass.
Yeah. Yeah, exactly. Yeah. So, and for example, well, I'll get to this in a second. So you can, for all a small, you can choose t that kills off lambda 1. So what that means is all you have now is the second term, p of theta equals some cutoff function times the metric. And then, just as I said, for structural reasons in the equation, you can just do some integration by parts argument and show that lambda 2 has to be 0. So you've actually found a real 0. So that's why I said the catch is you need this extra degree of freedom for t, and this is exactly why. Okay, so now put it all together. Here's the actual statement. So the following four manifolds will admit a toric, well, I should say toric and C2 action invariant BT flat metric. So you can do CP2 connects on CP2 bar. Did I repeat myself just to be safe? No, you know what? This is a complete, wow, this is a disaster, yeah. So it should be S2, S2 cross, you know what? No, it's okay, I don't need to because it's down here. So, so I don't know what I think I did a cut and paste here and I got a problem. So here's the table. So CP2 with CP2 bar, S2 cross S2 with CP2 bar, and 2 copies of S2 cross S2. Now, again, so you choose this T to kill off the leading term. Now, so when A is really small, the value we choose of T will be very close to this value. And so for these manifolds, because everything's explicit and you can choose your coordinate system explicitly and actually calculate everything by hand, these are the values you get for T0. So that value, although it's a funny formula there, it turns out for these explicit examples, you know it. You know exactly. Now, in this table, by the way, this formula for T0 involves the mass. Now, for CP2, when you blow up conformally, that's known as the Burns metric, and the mass was known. Right? You can write down everything very explicitly. So, but for S2 cross S2, the mass was not known. This drove my co-author Jeff crazy. So he wasted, well, I should say, he spent a lot of time. And sorry, I didn't mean it. It's one of those things where you get obsessed with something because you're convinced this can't be that hard, right? So you sit down, you start calculating, and you realize, yeah, it's actually harder than I thought. So I walked away, and then Jeff really stayed at it for a long time, and then he called me quite exhausted and said, okay, I know what the mass of S2 cross S2 is. So he wrote it up, so it's about to appear. So anyway, you know it, but it's not something nice like square root of 5 or something. You have to write it as some series. But so the numbers I gave here are based on his calculation of the mass of S2 cross S2. So now you can do other gluing configurations, by the way, by imposing other discrete group actions. So basically you have, because, for example, in S2 cross S2, you have, 4 fixed points of the torus action. So you can use those as gluing points and impose other invariants and get different gluing configurations. But it takes a little time to explain all that. So let me go into that. And then let me just end. Okay, yeah, perfect timing. Okay, let me just end with point out sort of a strange dichotomy that this implies. So for every small value of the gluing parameter, we catch a critical point. So there's lots of critical points, it seems. Or maybe there's not. So that's the dichotomy. So either for values very close to T0, you always have a critical point. Or what happens is there's only, in that expansion I showed you, the only critical point you ever catch is where T is exactly equal to T0. And therefore, the choice of gluing parameter just amounts to a moduli. So maybe you really just have one solution, but you caught a moduli space. Right? Or maybe they're geometrically really different metrics. We don't know. But this is something that we're trying to understand right now. What you have to do is look at the next term in the expansion. So let me flip back. In this expansion here, maybe that O of 5 term isn't there at all. Right? And so in which case, once you choose T to be this special value, you already have a 0. And doesn't matter how you choose A. Right? Or maybe there are different critical points for different values of T. We just don't know. we're trying to go deeper into the asymptotic expansion, but it's these calculations are tough sledding. So it's not clear we don't understand this, but it's something we're actively working on. Okay, I think I'll stop there. Thank you very much.
You just mentioned a few manifolds that you could build in this way, but presumably you can add an arbitrary number of summands while keeping the symmetry?
It can't be arbitrary because we have to, we'll need to do it along fixed points of the different actions. Otherwise you run into trouble, right? So that's why I didn't want to state it, because it gets a little bit complicated. So there's a table, we can talk here. I can show you the different ones you can do that preserve the symmetries, and we know we can write down everything in the approximate metric in an invariant way and define everything. So it's a finite number, but it's a somewhat complicated list.
The first several that you wrote down, we already knew that there were Einstein metrics on P2 connected on P2 bar or CP2 connected to CP2 bar.
Right, there are examples.
And they have all the,
right.
They have all the symmetries you're looking at.
Right. But there are examples.
S2 times S2 is not one that's.
Right. And there are other examples where for sure there's not.
Other questions?
Usually when you have a gluing theorem, there's an accompanying convergence theorem with a bubbling.
Yeah, okay. Yeah, that's a very good point. So I guess this would fall, I mean, a number of people have looked at these, for example, Tian and Viaclovsky wrote a series of papers on critical metrics for four manifolds. So I guess that would be the corresponding convergence theorems for this.
How does the scalar get multiplied by the ADM mass in that equation?
It's, okay, so what you end up having to do is, when you calculate, so how do you get that formula at all? You solve, okay, so you solve basically BT tensor equals multiple of the co-kernel. And you'd like to show that multiple of the co-kernel isn't there. So you pair both sides with the co-kernel and you integrate. Now how are you going to find out what anything is? I mean, how do you know the value of anything there? You start expanding. You write out basically an expansion of the BT tensor using it basically right out its first few terms of its Taylor series. So you need to know the first few terms of the Taylor series of the metrics. While for the asymptotically flat metric, it's the asymptotic expansion of the metric near infinity where you see the mass. So that's why the mass has to come in a very sort of vague way.
Other questions?
Yeah, it seemed like the second element, the second co-kernel guy, the conformal killing operator on omega 1.
Yeah.
That seems like a pure gauge term. So it shouldn't appear in a co-kernel. But
yeah.
Is it the weight function space, which is?
Great question. So it's because of its growth. So it's exactly at the level where if you try to do some integration by parts to show that term, see it should be, let's just take the simple case. Imagine you're looking like Bach equals conformal killing. Those are orthogonal things, right? One is transverse traceless, one is in the, so but because of the growth of the conformal killing part, if you pair them and try to integrate, you'll get a boundary term which is non-zero. So that's a great question, but that's exactly what's going on, yeah. That's when we first saw it, we thought, oh, we're done, right? And then we realized, no, we're not even close to done because of the growth. Yeah.
If there are no other questions, let's thank our speaker.